So interesting presentation by Vint about the interplanetary internet exchange. So I won't start about interplanetary quantum internet exchanges. That's still even further out. So Melchior Aelmans, I work for Juniper, and I'm part of the service provider architecture team, and I also lead a team that is doing research into the quantum space. What we're trying to figure out is what does it mean to networking, right? This whole evolution of a quantum computer, is it something we should develop technology in ourselves, or how should we address the potential quantum threat once a quantum computer exists that is powerful enough to successfully attack encryption we're currently using. So some of the stuff I'll talk about might be not there yet or might not come. So basically this says don't buy anything based on what I'm telling you today. And what we'll look at is why this is starting to become relevant. You might all have heard about this quantum computer that is being developed. There's a lot of research and also a lot of commercial parties that are looking into building a quantum computer. Some believe the quantum computer that is so powerful that it can actually successfully attack our current encryption mechanisms might never exist. The current prediction is, I think, 25 years, so we're still a bit out. But they said that 10 years ago as well, right? So the question is, when will it ever exist? However, the interesting thing is there is a lot of regulation and legislation starting to appear around the globe that at one point simply will force operators and those who transport data and use or have sensitive data to at least secure that in a quantum safe fashion. So we'll look at what is happening in some of the theaters around the world. We'll look at what options you have today and what is coming. So what is the problem, right? If a quantum computer ever exists that is powerful enough to run an algorithm, which is called Shor's algorithm, then it is able to successfully attack algorithms that we're using today, like Diffie-Hellman, right? Diffie-Hellman is being used in IPsec, in IKV2 to exchange keys, right? So public key infrastructures, asymmetric encryption, those are potentially vulnerable to this quantum computer. Why? Because a quantum computer is supposed to be very good at factoring prime numbers, right? Multiplying prime numbers is fairly easy. A classical computer can do that very quickly. However, factoring a prime number or factoring a number back to the prime numbers is something a classical computer has, is a very big challenge to a classical computer. So the simple answer is just switch to symmetric key cryptography, right? However, the challenge with symmetric key distribution, for example, is that the way it's currently being done is by people flying around the world with suitcases with key material, right? You probably all know how it works in DNS, right? Where there's an actual key rollover. Being done by people physically on the ground. That works if you have a few root DNS servers, but it doesn't really scale if you have a lot of home workers, right? Or people traveling. And the answer is symmetric key cryptography because there is no attack vector, right? It's not using Diffie-Hellman or any other potentially vulnerable algorithm. So that's one of the answers, but it's not that easy. Or there are solutions being developed and there are solutions already available. Some of you might have heard about solutions like quantum key distribution. We'll get to that later in the presentation. And there's things like PQC algorithms, right? NIST in the US has just finalized a competition where they selected a few algorithms that are supposed to be quantum resistant. But as I already mentioned, it's probably not even the quantum computer that is going to be the driver, let's say, for quantum safe communications. It's even more legislation and guidelines being published. Some are more strict than others, like, for example, in the US, the NSA stated that if you, in a few years, want to exchange data with the US government, you have to do that in a quantum safe fashion. Here in Europe, we're seeing similar advisories still, so they're not that strict, but basically they all suggest that at one point you need to start implementing and using communication methods that are quantum safe. it is obviously expected that at one point advisories become legislation, and there will be potentially fines, for example, as well, right? That's what we're seeing with a lot of legislation development. And interestingly, a lot of countries, Western countries, they in general have legislation that gives you the right to use encryption, right? So, for example, in our countries, it's everybody can use encryption, right? So if we specifically focus on one of the countries, I took Finland as an example. It's literally stated that everybody can use encryption how they wish, using any technical possibilities available, unless otherwise provided by law. Basically, you can encrypt whatever you want, but also legislation in Finland states that if the law requires anyone to hand over passwords and decryption keys, if necessary, to conduct a search of data, etc., in the course of criminal investigation. So in other words, if you have possession of the key material, for example, from your customers, if you provide security services, then you could be forced to still hand over that key material. It's a bit of a sidestep. It doesn't really relate to quantum itself, but if you look at other legislations, probably we all heard about GDPR, the data protection regulation, that already imposes strict penalties if you're not compliant, right? Up to 4% of annual revenue. That's the beginning. And the next step is the e-privacy legislation that is becoming even more stricter. But also NIS2 directive, the Digital Markets Act, etc. So a lot of legislation is appearing in Europe, in UK, and in other parts of the world that in some cases suggest about the use of quantum safe encryption, but at least becomes more strict, and as you just saw, could imply fines if you don't comply or if there's a data breach. And also, for example, looking at the White House directive and what others are doing, they're all hinting towards, at one point, you have to use a post-quantum or quantum safe encryption. BSI in Germany, same. The examples go on and on. NCSC, prepare for quantum safe, etc. But it's not that easy, right? A lot of people I speak with who have heard about the NIST competition might think that now that NIST has announced these 3 quantum safe algorithms, that it's the vendors implementing it and you're done, right? But just implementing a few new algorithms has quite some impact. For example, this is a very brief overview created by Entrust. If you look at the right side of the slide, you see stuff like HTTPS, QUIC, DNS over HTTPS, etc. They don't need updating because they rely on other mechanisms, right, which you see on the left side. For example, TLS, SSH, etc. They define their own crypto. So all these protocols, all these tools need somehow updates, right? IPsec, we already mentioned, is using Diffie-Hellman, for example, which is not quantum safe, right? So it's good that NIST has defined these, but there's a long way or long road still to go before we can actually use them in our networks and in production. So what are the options, right? Migrate to PQC today. There are vendors and also some implementations by Google, for example, and others that already have done some of the work for the post-quantum algorithms. But the question is it already that wise to simply rely solely on PQC algorithms, right? Because the real threat is not even there yet. The real threat, the quantum computer, doesn't exist yet. So switching fully to PQC might expose new risks. Apart from the quantum computer, it could also mean risks, for example, implementation, etc., right? We've been using algorithms like Diffie-Hellman for the last 20 years, right? So all the attack vectors, all the implementation errors you could have made are found and addressed by now. Do nothing could be an option. If you are sure that your data in 20 years has no value anymore, then it could be an option to do nothing, right? For example, the number I have on my bank account today is probably not really relevant in 20 years anymore, right? But if you have missile silos, like some defense organizations have, for example, you're not moving them probably in 10 to 15, 20 years, right? So it depends a lot on what the value of your data is as well. And the third option is a hybrid approach, right? So either combining classical algorithms or like Diffie-Hellman with, for example, additional key material, or combine PQC with classical algorithms. There's a lot of work going on in standards organizations already. For example, what a lot of vendors, including Juniper and others, have done is to implement RFC 8784 that basically describes how you can supplement IPsec with additional key material. Right, so you still have the Diffie-Hellman key exchange, but on top of it, you supplement that with key material you received out of band, for example, from QKD or some other mechanism that distributes key material. If you would implement this, or if you would use this, you are considered to be quantum safe according to NIST, because if somebody would attack the Diffie-Hellman key exchange, then he only has a part of the key material, right? So not the out-of-band exchanged key material. So that is one option. But what about things like MACsec, for example? The good news is that MACsec on itself is quantum safe because there's no key exchange in MACsec, right? You configure a key on both sides of the connection and that's it, right? There's no key rollover, but that exposes new potential security vulnerabilities as well, right? If you never roll over the key, that's a potential security risk as well. So there's some folks are trying to drive, for example, in IEEE, where MACsec is standardized, also a mechanism to come up with a way how you can take in this external key material and mix it in MACsec as well. But on itself, again, MACsec is considered quantum safe because the encryption itself relies on AES 256, which is considered quantum safe. So that's already a good start to, let's say, enable MACsec on your networks on your backbone. So what are the options if you would want to, let's say, indeed become quantum safe? There's basically three options, right? One I mentioned is the use of these post-quantum algorithms as defined by NIST. The second is to use mechanisms like quantum key distribution based on physical hardware and boxes sending polarized photons or qubits in between. And the third is to mix symmetric keys that you receive out of band in IPsec or other protocols. So let's focus first on NIST. As I mentioned, NIST has now published the three finalists. But as you can see in the timeline, there's quite a big gap between 24 and 28, 29, which is the adoption phase of PQC, right? As I mentioned, it's great that NIST has announced them, but now all the standards bodies like IETF, IEEE, ETSI, GSMA, etc., they need to update their standards as well. And then vendors like Juniper and others need to start implementing this, right? And a lot of the vendors will only implement once the standard is there. Everybody's already scoping the work and trying to assess what the impact is, obviously, but the real implementation you can only do if you have a standard. So the NIST PQC algorithms might still be quite some time out. So the good thing is that currently today, traditional PKI scores pretty low on the risk scale, right? You can see on the horizontal scale is the risk, and the vertical scale is the risk, and the horizontal scale is the timeline. So today, traditional PKI is still considered to be safe, right? There's, except from so-called store and decrypt later attack, where some entities, some governments might already store data today with the encryption, with the intention to decrypt it later once a quantum computer becomes available. We're at this point now where the, let's say, implementations are starting of the NIST PQC algorithms, and you see they score pretty high on the risk scale. Why? Because, as I just mentioned, the real threat is not there yet. We have not seen much real implementations or much use in actual production networks, so there hasn't been much attacks yet against the PQC algorithms. Obviously, once the as it's called, the cryptographically relevant quantum computer exists, then the whole equation changes, right? Then hopefully the NIST PQC algorithms are score lower on the risk scale because we've seen some implementations and we found bugs and addressed them, etc. But by then, traditional PKI scores very high on the risk scale, right? Because then the real attack vector is there. So over time, we'll see obviously a migration towards PQC, but again, this timeline could, and that's intentionally why there's no dates, this could still be, let's say, 5, 6 years, maybe even longer out, right? And the quantum computer itself, as I mentioned, is probably still 20, 25 years out if you believe the experts. But yeah, over time, traditional PKI as we use it today will disappear and quantum-safe algorithms will take over. But there's, apart from the work that needs to be done, there's also a few challenges with these PQC algorithms, right? How resistant are they against classical computers, for example? There has been one of the finalists in the NIST competition, the Psych algorithm, was considered to be quantum safe, but it was broken in 62 minutes on a laptop, a classical laptop, right? So now we have quantum safe algorithms which are potentially not safe against, let's say, classical computer attacks. But also the implementation complexity is way more than for the algorithms we're using today, right? It's expected that the number of lines of code is at least around 50% more than for the classical algorithms, right? So not all network equipment or in general equipment being used today in encryption is able to run these new algorithms. And the key sizes are much larger, right? So it could be that not all network equipment can store the keys. So there's quite a few challenges here before we can finally or fully migrate to PQC. So the second option, a quantum key distribution. This is a mechanism, as I mentioned, based on hardware. So you have two boxes with the dark fiber or wavelength in between. Where the biggest challenge is from a technical perspective that you cannot amplify these polarized photons, right? Because without going too deep into quantum physics, but if you polarize a photon, if you bring it into a superposition, you cannot amplify it anymore. So, because if you amplify it, you change the quantum state. So, QKD solutions are available from Toshiba, ID Quantique, and a couple of other QKD vendors. But it only works in the metro, right? So you could probably span the metro London, but London-Amsterdam is already a challenge, right? And I know there are satellite-based QKD solutions, but they pose their own challenges. But this is available, so how it basically works is you have two boxes, Alice and Bob. One always sends polarized photons and the other detects them, or is the receiver, has a photon detector. And we have two routers, in this example Juniper routers, could be others as well. And we have a few connections in between them. So between the QKD boxes, as I mentioned, there's either dark fiber or an unamplified wavelength. That is used as the quantum communication channel. So polarized photons are being sent from Alice to Bob. And they need a classical channel to do synchronization and exchange of filters and stuff like that. And between the routers, we have, in this case, a MACsec secure data link. As you know it today, right? The MACsec implementation itself didn't change at all. So now if we want to start using this external key material, we built a script which is still in the proof of concept phase that actually requests from Alice QKD a key. It receives a key and a key ID. Now we install the key into the configuration and we send the key ID to the other side. You can do that in plain text, unencrypted, because with the key ID itself you cannot do anything, right? And with the key ID, you cannot decrypt the communication. But we use the key ID on the other side to request the key from QKD as well. If we're lucky, we receive the same key, install it into the configuration, and now you have a, let's say, a quantum-safe MACsec link. Interesting here is that this QKD system that keeps on generating keys, right? So you can roll over the key now automatically as well, which, as we just mentioned earlier, is an additional security mechanism. There's different vendors, Juniper, others who have implementations. The downside here is that this is not standardized yet in IEEE, right? So it's not, you cannot currently use a Juniper in a Cisco device, for example. The interesting thing is in IPsec, as I mentioned, that is standardized, right? RFC 8784 specifies how to do this. Again, we have 2 QKD boxes, and in this case, we have 2 firewalls. But now, within the protocol itself, if you define into the configuration that you want to use additional key material, and the way it works is LS firewall now indicates to Bob firewall that its willingness to use keys from QKD in this case. Bob acknowledges that it's also willing to use that key. And then a key request is sent, basically the same as we just saw in the MACsec implementation. So we receive a key and a key ID, we install the key into the crypto engine, we communicate the key ID to the other side, request the key on the other side as well, receive a key back, and acknowledge that we're using the key, and now we have a quantum safe IPsec connection. As again, this is standardized, a couple of vendors have done this, so this is actually something you could already use today. The third option is symmetric. I'm going a bit fast because I'm running out of time, I see. Is symmetric key establishment. It's a mechanism that basically delivers you the same as QKD, so it delivers keys in multiple locations, but without using any quantum itself. It's all based on software. In very short explanation, without going too deep into it, how it basically works is we distribute pre-shared random data to Alice, Bob, and Charlie in this case. And now if Alice and Bob want to form a key, they use what's called security server in this mechanism, in the distributed symmetric key establishment solution. It sends a key instruction via one of the security servers to Bob, indicating that it wants to form a key with Bob. And what they do next is, out of that pre-shared random data, they form a key with an algorithm that runs in the container itself, right? So there's no key exchange. There's a white paper on this and an IETF draft, how this works, for those who are interested. But the reason why this is considered quantum safe is because there's, again, no key exchange, right? So you construct or you establish keys in 2 locations without communicating the key itself. And the way to use it is exactly the same as we just saw in the examples with MACsec and IPsec, right? So instead of having 2 QKD boxes, you now have 2 containers or even daemons running on the box, potentially, that can deliver those out-of-band keys. And we've did some tests with our NFX350, which is Juniper's x86 platform, to run it all in one box as a sort of a quantum safe CPE solution. So you see more of these things coming from the different vendors, first as proof of concepts, but going forward, let's say maybe these are the first steps to the quantum internet at one point, or the quantum internet exchange. So the conclusion, although legislation might sound a bit boring, I hope I didn't spend too much time on it, but it has impact, right? And they are becoming stricter advisories and legislation at one point where you would need to comply to. So start looking into it today. Start thinking about the value of your data. As I mentioned, what is the value of your data in 10, 15, 20 years? Start doing proof of concepts, right? Juniper, other vendors have all capabilities to do proof of concepts. There are, as I mentioned, QKD solutions available. There are symmetric key establishment solutions available. We slowly see some PQC implementations become available as well, so start building that knowledge. And if you're interested, there's a lot of work still to be done in the standards organizations. As we saw in MACsec and how to communicate those key IDs, etc. There's a lot of work to be done. So if you're interested, join that work in IETF or other standards organizations. Do we have time for questions still, or am I too far over time?
Oh, we've got, 1 or 2 if there's any. Yeah, Sharon, over there.
Hi. You spoke about RSA-based Diffie-Hellman key agreement compromised by quantum computing. What about the other standard that's used, which is the elliptic curve Diffie-Hellman?
Yeah, elliptic curve is vulnerable. Yeah.
Is that also projected to be compromised with quantum computing?
Yeah, elliptic curve Diffie-Hellman is vulnerable to a Shor's algorithm. Yeah, that's correct.
So that's also predicted to be broken?
Yeah. Okay. And I think the latest NIST guideline that was published a couple of days ago that indeed says that by 2030, from top of my head, you should not be using that anymore.
Not even elliptic curve.
So that's already pretty fast if you look at the life cycle of network equipment, etc.
Thank you.
Sure. Any other questions, or is everybody asleep?
No.
All right.
Okay. Thank you very much.
Thank you.